Yeah, hello everyone. Hope you can hear me and see the screen. I'm Hariharan Ravishankar. I'm a chief AI scientist from Intangles Lab Private Limited. Today I'll be representing a great bunch of team that we have in Intangles, and the topic will be predictive analytics for mobility. So this is how the agenda will be. We will first introduce what Intangles does and why Intangles exists. So the key answer to that question is the whole paradigm shift from reactive to predictive analytics. I'll walk through few examples of AI vehicle component monitoring using the industry-leading digital twin and AI technology. And then I'll get to few solution snapshots at a very high level of how the whole ecosystem of hardware and software comes together and entangles. And finally, I will delve deeper into one particular problem for which we have benefited immensely from AWS solutions. So Intangles is an 8-year-old company starting the operations in 2016. So the key mandate for Intangles is to be the leading predictive analytics solution provider for the mobility industries. And we have a huge expertise in predictive analytics, which is a combination of AI and ML and statistical inferring processes. And we are also highly agnostic to the fuel type. So we don't only cater to IC engines, but we also have ventured heavily into the electrical vehicle analytics as well. All this is enabled by a hybrid compute platform, which includes custom hardware, proprietary hardware, as well as very interesting software and visualization components that bring together the analytics insights that we are talking about. We are also highly interested in AI on chip. So the way the world is moving towards, we want to get predictive analytic capabilities on the edge as well. That is also in the roadmap of Intangles. We don't necessarily stop with vehicle health predictive analytics. We also play in this entire ecosystem of multiple players. This includes insurance players, tires manufacturers, battery folks, and logistics people, and also the after sales of used vehicles. Intangles is growing at a rapid pace. We have grown to have staff in 8 countries, and we have operations in multiple countries, as the dots are showing here. And this is one of the key things that I'll talk later. So, how do we go live in a new geographical location is something that I will highlight as part of where AWS is helping Intangles. So we are a data company. This slide just tells us, the scale of data involved. So there are a bunch of vehicles that are shown on the left, and then there is a proprietary hardware OBD device that collects the 400 odd signals from each of these devices. And as you can imagine, this will be highly unstructured, and there's a lot of processing and storage components that go into convert this unstructured data to be curated and enhanced, and finally be consumed for AI applications. Just to give you a scale of the data involved, we roughly, for a fleet of say 150,000 vehicles, we collect close to 18 billion time points per day, and we manage close to 60 terabyte of data. And this translates to lots and lots of predictive alerts, close to like hundreds and thousands of them. And this indirectly like translates to many benefits. One of them is the tons of carbon dioxide emissions saved, and also ensuring that the accidents are prevented in terms of say the safety of the whole driving behavior and fuel theft and so on. So at the core of Intangles is this digital twin technology. So Intangles tries to build the holistic view of the asset. The asset could be a customer truck or a bus, by making digital twin components of each of these components. So each engine, be it ICE or any other type of engine, is made up of thousands and thousands of components. See, the goal of Intangles is to build these digital twins of each of the components, enable the predictive analytics on them to ensure that the requirements and optimizations in terms of your fleet efficiency can be managed. So how does it translate to end customers as results? Firstly, when you are in the predictive realm, you foresee the potential of breakdown, and biggest benefit is the increase in uptime. So close to 75% of reduction in breakdown events, and it leads to roughly, say 10 to 30% of asset availability. And there is also a reduction in maintenance costs, because if you are in the predictive world, you find these faults before they occur, and it's much easier and simpler and cheaper to replace or attend to the faults before the part actually breaks down. And we also ensure that the performance of your vehicle improves. So the for the same amount of fuel, you get higher mileage, and that leads to a big saving up to say 10%. So, what is this fundamental philosophy that is driving all these, sort of great insights? Is the paradigm shift from reactive to predictive. So, the almost all the existing solutions in the market look at a truck on the road, and as you might have experienced with your passenger cars as well, you get these signals only when the situation is already out of control. So it could be a battery alert, or it could be an oil pressure alert, or it could be anything else, right? So this is what we call as diagnostic trouble codes. So diagnostic meaning it is a diagnosis after the event has already happened. And this might have already led the vehicle to break down. But what Intangles does is it continuously monitors the 450 odd time series data that I spoke about. So we do multivariate time series analysis on very large data, and we constantly are monitoring the abnormal behavior in those signals. And this allows us to detect an issue before it becomes very serious. And these gaps allow you to act in time. Sometimes it can be hours ahead, it can be days in advance, and it really allows you to act before the part breaks down, hence ensuring that you don't suffer the catastrophe of your asset not being available and so on. So these are some of the examples of the different digital twin components that get built as a combination of AI and physics-based modeling. So it includes, engine coolant temperature, battery and alternator. How does your turbocharger work? How does your components of your exhaust system work? And we also have a great algorithm for accurately predicting EV range prediction and so on and so forth. So I'll just walk through one particular example as to how predictive really helps. So I'm going to take this example of engine temperatures crossing an ideal range. I'm sure many of us have faced this. Suddenly the engine overheats and you have a breakdown on the side of the road, right? So what we do is we model the engine temperature via a surrogate signal, which is the engine coolant temperature. So this is how the time sequence of the events happen. So we continuously model the component using the physics underlying physics. So in this case, it is pretty clear that there should be an expected relationship between the engine coolant temperature and the load that the vehicle goes through. So we constantly monitor it. There are other multi-parametric solutions that are involved here. I'm oversimplifying it a bit, but when we are monitoring the asset, you can see that say around Jan 9th, 12:47 p.m. everything looks good, but what Intangles does is it has detected some minor alert around Jan 10th, 11:46 a.m. And I have skipped a bunch of steps in the middle in the interest of time, and it progresses to say minor to next state and then major and so on. But what we really see is that the engine control unit, which produces these diagnostic trouble codes, actually has raised an alarm at Jan 10th, 2024, 5:14 p.m., right? So there's roughly 6 hours gap that you have. And this is the power of predictive analytics. And we don't stop here. We don't only get ahead in time, we also provide evidences and recommendations. So these recommendations allow you to take appropriate actions. In some case, it could be to say, go to a nearest service station to fix it, or in some other case, it might be to ask you to check something else and so on. So all this is brought together by three factors. One, the large scale data that we work with, the physics, underlying physics of each of the components that lead to the digital twin modeling, and finally the AI. I'll get to the end-to-end system. How do we sort of say achieve all this? Firstly, like I said, it starts with a custom hardware. So we have our own device which taps into the CAN port and samples these signals at a high fidelity rate. And our solution is industry standard in terms of, say, resolution as well as quality of data. And this goes into a backend infrastructure. I'll expand on it very little bit, but I'll not be getting into much of the details for obvious reasons. But there is a huge, sort of architecture that handles many, many things. As a principle, we like to design all these components in a cloud agnostic way, but definitely, AWS components play a big role. I'll highlight on them a little bit later. And then it goes into analytics, like I said, physics-based AI. And one of the key things that really also happens is continuous learning. So since we have diagnostic trouble codes continuously logged as part of our system, we have a capacity to evaluate our algorithms capabilities on the fly. So if we make a prediction and if a corresponding diagnostic trouble code comes immediately, then we say kudos to our algorithm. But if it doesn't happen, then we can go and fix, why and what happened there. Why did the DTC not come? Why is it a false positive or a false negative? And continuously, like update our solutions. And we also are high on ensuring that regulations are met. So there is a lot of like thought that goes into the whole design of each of the components that are listed here from a regulation perspective also. Finally, the insights are translated or transferred to the end users via proprietary visualization platform. So it can be a website or it can be a mobile phone. But this is where the users get to enjoy the fruits of the predictive analytics. So this is a architecture prototype. I'm obviously not sharing the latest architecture for many reasons, but we have this prototype to explain how different components come together. So some of the AWS components that you see here might be from previous generation. For example, we have exclusively moved away from DynamoDB to S3 based storages and so forth. But this architecture is only to explain, how data flows and what are the different components. Even though I have spoken exclusively about vehicle health predictive analytics, Intangle's goal is to provide a holistic suite of predictive fleet analytics as well. So vehicle health prognosis is one part, diagnosis is another part. But as you can see, the huge components, other components are listed here. One of it is driving behavior modeling. So you will see that there is a big architectural component that ensures that driver safety score and driving behavior score are getting computed for every trip, which means that you already also have to track the trip data. That involves so having your own trip database and different services that are related to it. And you also need to give feedback to the end users on operational efficiency. So you need to understand the geospatial implications. For example, the same fleet which is highly performing on a summer might do very poorly on winter because of say various reasons, say the challenges in driving. So we have lots and lots of algorithms that take into account, say, location based information as well. And we also have live fleet monitoring. So usually our customers have a command center where 24/7 they are monitoring the live incidents that we produce as part of both driving as well as vehicle health, and they immediately contact say the supervisor or the driver and fix it. So there is a lot of live components that go into it. In short, AWS components play a role in all of these things, and this is a previous generation prototype, but I just wanted to highlight the complexity and interaction between different components, both from the functional perspective as well as from the architectural component perspectives. Finally, I wanted to give a live issue that we really benefited from AWS EKS solutions. So as Intangles is scaling up to new demographics, one of the key component for converting a pilot into a sales order is how fast can we go live, right? So this is what we call as speeding up the go live problem. Oftentimes, when we meet new customers in new countries, they usually judge your solution by how ready are you to scale to their geographies. So this is a very, very, very important factor in converting sale orders. So what we really wanted to do is we wanted to automate this whole process of going live. We want to seamlessly scale across regions. And on top of it, speed alone is not the criteria. We also want to ensure that the deployments are reliable. It often gives a very bad look when you have gone live in a new region and then suddenly something breaks down. So we need to also incorporate a lot of fault tolerance technologies there, and we also want to ensure that security is in no way compromised, right? So few months back, this is what we call as Gen Zero or Option Zero solution. We used legacy non-Kubernetes solutions, and this had so many issues. So it was, first of all, it was highly time-consuming and a manual process, and there was a lot of administrative burden to manage different facets of the solution, right? And this includes scalability, statefulness, security threat, and so on. So team did move to the intermediate solution, which is a self-managed Kubernetes. It did help in a big way, but still, it was tough to manage all aspects of the Kubernetes platform. Specific issues included setting up upgrades, catching up with the upgrades, ensuring that like fault tolerance mechanisms are in place, and also compliance standards are in place. So this is when the software engineering team took a call to explore AWS Elastic Kubernetes solutions, right? And we couldn't be more happier here. So first of all, migration to AWS EKS has relieved managing different aspects of Kubernetes solution, right? It comes as a integrated package where each of these facets are managed automatically. And one important point that my VP actually wanted to highlight here is that uh, we were not a Kubernetes ready company from a skill perspective, right? So we didn't have like major experts who have worked on it. But AWS EKS was so easy; it had low technical barrier of entry, which means that there was absolute ease in migrating from vanilla self-managed Kubernetes solutions to EKS. And the added fault tolerance and security, since all these microservices run inside a dedicated cluster, came as a bonus, and we were very, very happy with it. And we also generally found that all this lead to more faster and a reliable and a graceful deployment of the application. So again, this is a direct quote from my VP. So the time to go live to new locations drastically reduced from say 4 to 5 weeks to less than a week. And this less than a week often means few days, 2 or 3 days, but the other days are used for ensuring that QA checks are done and so on. So this is a real use case where we have benefited from. So I'm not sure how I'm doing on time, but that is mostly what I wanted to cover in this talk. And any questions, I can happily take them.
Hey, thanks, Hariharan. I think this is an amazing journey from reactive to predictive, and it was amazing to learn more about how you were able to go live in new regions. So we have two questions from the audience. Karthik wants to know: are you using a product twin at a component level or a system twin?
Sure, that's a great question. So we do both. So it is, you can think of it as, firstly, the first level of digital twins are at a component level. So like I said, in a typical engine, there are thousands and thousands of component. The aspiration is to go and make a digital twin of each of the components. But then there is a second level, which is at an aggregation level, where these digital twins come together and form a system digital twin. So the answer to the question is that there are both levels of digital twins that are being used. And one more thing that I wanted to share here is that since there are thousands and thousands of component, it's really impossible to take the traditional routes to build these digital twin components. So that's where, as a futuristic step, what Intangles is currently doing is to bring physics, AI, and generative AI also into play. So we think that can unlock the scale for us.
And there's a follow up on that. How are you generalizing the components?
I might need little bit more detail on that question. So I don't understand what does generalizing the components mean, but I'll give my interpretation. Um, So is the question that how do we know that the same set of components come across different vehicles or not? I don't know.
Yeah, let me try to unmute all. I don't know if
Yeah,
yeah, just try to unmute. Karthik, if you want to unmute yourself and ask the question. Yeah, can you try unmuting yourself? I don't know if you are able to. If not, just type your question in the chat. Okay, so I think this is only for the panelists. Sorry about that. Maybe participants
sure,
should be able to unmute themselves.
no problem.
Yeah, I think while Karthik answers that, there's another question from him.
Yeah.
Are you using the generic ODB data or CAN data from vehicle? If it is CAN data, are you working with the OEM to deliver these solutions?
Yeah, so we are working with the CAN data that our device directly taps through the OBD port. Okay, so that's where really the uh, benefit of high fidelity and data quality comes. So in terms of our go-to-market strategies, we do both uh, OEM integration and aftermarket solution. So we are highly coupled with Mahindra. So all Mahindra devices, I should not say all Mahindra assets, at least in the truck and bus, has our solutions part of it. So that is the OEM play, and we also have a huge aftermarket play on customers like Volvo, Acer, and so on. So I removed the slide on our customers, but pretty much like every player, both nationally and internationally, we serve as a aftermarket. But with Mahindra, we are OEM play. We have the OEM play.
Okay.
Yes. So the now I understand the question. So our digital twins are highly aware of OEM, highly aware of the spec. For example, what could be a spec? It could be dependent on, say, the tonnage of the vehicle. It could be dependent on the type of engine, whether it is a Cummins or a Packard, and it also is highly dependent on OEM. Since we have the luxury of data, we are able to do analysis specific to each of the vehicle from its corresponding peers. We don't generalize across vehicles. Driving behavior is something that we can generalize, but otherwise, we are very, very aware of the differences of the components for a particular spec. And, we ensure that the modeling is the digital twin is highly specific to that class of vehicle.
Okay. Hope that answers your question, Karthik. I see he had also put an example. Okay. Sure. And I had some questions. I think we are good on time, so I'll try to pick your brains for a few questions. One is, you mentioned about sustainability. So I'm just curious, what AI features you're using for monitoring impact on the environmental health in terms of sustainability and carbon tracking specifically?
Sure. So what we have realized is that the exhaust subsystem of the engines have become the highly crucial components from a couple of perspectives. One, the regulations, if you see all the BS4 and BS6, all of them are highly like dependent on the exhaust subsystem. So one of the ways that we are approaching this problem is to model this exhaust subsystem in a holistic way. This again goes back to the component level digital twin to the system level digital twin. So that's the first component. And secondly, we are ensuring that we have AI algorithms that monitor different types of these harmful pollutants. This includes, say the high nitrous NOx emittents, and we also have a great AI solution which recently got released and got a lot of press on particulate matter, right? So this diesel particulate filter digital twin solutions is there. So we ensure that each subcomponent of the exhaust subsystem is modeled as tightly as we could, and this is allowing us to ensure that our contribution to this whole environment sustainability. And as I said before, we are seeing benefits of generative AI in this. So unlike some of the other approaches where if you give a lot of data, I'll build a huge model. We are seeing the benefit of bringing physics and Gen AI together, and that is also helping us in ensuring we meet some of the goals that we have set for ourselves.
Great, thank you. And then, so you mentioned about the predictive maintenance solution. So I want to understand how different is it from the existing solutions where the engine light still goes on, when the maintenance is happening, right? So,
Yeah. So I think there are two parts to this question. First is we want to be ahead before the vehicle breaks down. So whenever you see a DTC, it means that it has already gone bad. And usually these ECUs wait for once or twice for this issue to come, which means that your thing has already become very bad. So the time component is a huge thing there. And secondly, as I mentioned earlier, we don't stop only with the time component. We provide them with evidence. Why is the why we think a particular alert is going to be raised? This is very crucial because in the predictive world, the acceptance of a mistakes made by a predictive solution is possible only if you explain the logic behind it. So we have to translate the AI predictions into a physics language that will tell the customer why we made this decision. Even though it could be wrong, even though the eventual event may or may not come, the fact that it's not a fully black box solution is highly important for the solution to be accepted. Thirdly, we don't stop here. We also ensure that actionable recommendations are given. Since we understand the physics of the system, we also can potentially give like remedies sorted in terms of say impact as thought by the AI platform to the end users. This means that they have a way to approach solving this problem in a stepwise manner, and then these three things sort of differentiate us against the diagnostic platforms.
okay, so it's about the data and the timing, how you
Right.
use that. And okay, great. And so this is a generic questions like, what are your next big bets for your solution in terms of technological
Yeah.
expansion?
Yeah, I think I mentioned some of it already. So we are bringing physics and Gen AI together. So we are very excited by that solution. We think it's going to be a platform technology, and it's going to seriously accelerate the number of components that we can monitor. That is our big bet. And we are also interested in uh, integrating video telematics solutions with OBD. So we'll be one of the earlier players to sort of bring an integrated view of them. And thirdly, we have high aspirations to explore adjacencies of mobility industry. So a combination of expertise in mobility and the whole platform that we are talking about, we feel this whole digital twin technology can be translated to other domains as well. As we make progress, hopefully in the next meetups or whenever, I'll be able to provide more details on them.
Awesome. We are right on time, but we have one more question. If you want to answer or answer it in the chat. So it's, what is the benefit you are seeing with digital twin when compared to traditional AI ML model running based on the data from telematic device?
So sorry, can you? Oh, okay. Yeah, so the whole idea is you no longer see the data points and only say some data points. Digital twin allows you to model the physics of the system. So the way we see it is, since you have say 450 signals and you're looking at a particular component, it can become highly unmanageable if you take the only a data centric view of the problem. So physics knowledge is an incomplete description of your component. It is essential, but it is incomplete. The laws of the physics are not there. These are purpose-built machines, right? You know that if your engine load is increasing, your engine coolant temperature has to increase. That much is what you can expect from physics, which is a huge leap to start with. It will help you to sort of clear say 60 to 70 percentage of the clutter when you have especially large data. But the rest of the picture, which is the actual relationship between these parameters, is supplemented by the data. So if you go the traditional AI ML route, you need large compute, you need insane amounts of data to first declutter. But with the digital twin concept, at its core is the physics of the component that you're trying to modeling. When you bring physics and data, you sort of get all the benefits that I spoke about.
Awesome. Thank you again, Hariharan. I think that was an amazing session, and